Today's lesson is going to be about acid-base reactions, which we reviewed during our honors chemistry review unit, but we just need to go into a little bit more detail during AP chemistry. So first of all, let's just remember that we have two different ways to write it. Bronsted-Lowry is where acids donate the H+, and bases receive that H+. Arrhenius is when the acids donate H+, and the bases donate OH-, and those two come together to make water. Another review of strong versus weak. Just remember that strong things break apart completely, or so close to completely that we consider it to be 100%. So you might see words like completely dissociate, which means to break apart. You might see completely ionize, which means to become ions, because when they break apart, they do become ions. And because strong acids produce and bases produce a lot of ions, they are good conductors. Weak acids and bases will stay together mostly, and then a few of those compounds will break into ions. So we consider them to be weak conductors or weak electrolytes because they do produce some ions, but not very many. Those 6 strong acids are something that it would be really nice if you could have handy. So if you could write those down on a sticky note or an index card and just keep it near your chemistry stuff, you'll use those quite often throughout the year. You'll eventually get them memorized, but for now it's helpful if you have them nearby. Strong bases are pretty easy. That's just groups 1 and 2 metals, so alkaline earth metals bonded to hydroxide. And I wanted to do a ionic equation for you because some of these are going to look a little different. If you have strong acids and strong bases, then when you write the ionic equation, the salts will all cancel out. Those will all be spectator ions, and you'll end up with just the H+ from the acid, the hydroxide from the base, coming together to make liquid water. And remember, it's liquid, it's not AQ when you have H2O. But if you have something that's weak, the ionic equation is going to look very different. And we haven't really done one like this, so let me just show you an example. So KOH is a strong base, and so this is going to completely ionize. So we can break this into K+ and OH-. But HF, if you notice, is not on that list of strong acids. So because it's a weak acid, most of these compounds are going to stick together. So we're going to keep it as HF instead of breaking it apart. If it's strong, you can't break it apart. And water is H2O. We're not going to break that apart because it's a liquid. And then KF is a salt. And remember, anything with group 1 is going to be soluble, so we can break this into 2 ions. So this is called the ionic equation, where you break apart any strong acids, strong bases, or soluble salts. And you can see that we actually only have one spectator ion for this ionic equation. The K+ is the only thing that is the same on both sides. And so we can take that out, and what's left in red is the ionic equation. And notice that it looks very different. It's not 2 ions coming together to make a solid like it was when we did those double replacement precipitation reactions. So not all ionic equations will look the same. All right, the next thing I wanted to do is a couple of these problems with acid-base reactions. So this was the first problem that was in your notes. It says, what volume of the acid is needed to neutralize a base? And it gives us a lot of information. So the first thing to recognize about this is that they gave us a lot of information about sodium hydroxide, but they're asking us what is the volume of HCl. So anytime you're given information about one compound, but you need information about another compound, you're probably going to do a mole-to-mole ratio from the balanced reaction. So the first thing is I wrote out the reaction, HCl plus NaOH, and it's just a double replacement. It's just a normal Arrhenius reaction. And it's all 1-to-1 because everything is +1 - 1. So it's 1-to-1 ratio. And then what I did is I noticed that I had enough information about the sodium hydroxide to find the moles of it. Almost always, not every time, but almost always when you see volume of molarity, you're probably going to multiply those because of means multiply. And when you multiply a volume times a molarity, you get the moles, and then you can do a lot of things with moles. So watch out for that in the question of volume of molarity. You're probably going to multiply to get moles. And that's the first thing I did in that fence. I took the volume of sodium hydroxide. Notice I turned it into liters because you need to be able to cancel the liters from the molarity ratio. Then I used the molarity, and you can see that liters cancels, and that gives me the moles of sodium hydroxide. Then I could use the mole-to-mole ratio to turn it into moles of HCl. And then at this point, you could have calculated this and then plug in the moles into the molarity equation. So if you know that molarity is moles over liters, once you do that fence, you can get the moles of HCl, and then they gave you the molarity in the question, and so you can get the liters from that. I just continued the fence because you can flip molarity upside down. So remember, molarity is in moles per liter. So 0.1 moles for every 1 liter, you can flip that upside down and fit it into the fence so that your units cancel. And that's what I did there. But either way you want to do it is fine. And then you get your final answer. Just watch your sig figs. Looks like we have 3 significant figures in the question, so that's why I left it as 87.5. All right, this next question was a long, tough one, lots of steps. So I went ahead and typed it out just to save time so I wouldn't have to write it, and because it's a lot neater than my handwriting with the stylus. So let me just walk you through it and I'll explain all the different steps. Let's look at the question first and see what they were asking. So they gave us a volume and a molarity of HNO3. So again, we're probably going to multiply those to get the moles. They also gave us the volume and molarity of KOH. And they're asking us what is the concentration, which is in units of molarity, of either H plus or OH minus in excess after the reaction goes to completion. So at this point, your brain's probably exploding and you're thinking, oh my gosh, what in the world are we supposed to do? All these numbers, all this stuff, I have no idea what to do. The first thing is, if you can write a reaction, sometimes that helps you see what's going on. You kind of can visualize the different chemicals and how they're changing. So we can tell this is an acid-base reaction. We've got an acid that starts with H. We have a base that ends in OH. So the first thing I did is I went ahead and wrote out the reaction. I balanced it. It's +1, -1, and now I can see what's happening. The next thing I noticed is this word right here, excess. That's kind of your clue that it's going to be a limiting reaction problem because we're doing limiting in excess. Your other clue is that they gave you a lot of information about 2 different chemicals. And you're like, well, how do you know which one to use? That's your clue that it's going to be a limiting reactant problem. So once you decide it's limiting reactant, what you need to do is take the information they give you about each different chemical, do 2 separate fences, and turn them both into the same chemical. So not into each other, but choose one of the products and turn them both into that product. And it actually didn't matter. I turned them into water, but you could have chosen KNO3 as well. The whole point is that you have to turn them into the same thing so you can compare which one produces more. So in this case, in that first fence, I took the liters of HNO3 and the molarity, and that gave me the moles. Then I did the mole-to-mole ratio to turn it into moles of water. Then I did the same thing with another fence, but I started with the other chemical, so the KOH. Again, turned it into moles, used the mole-to-mole ratio, and notice I did not turn it into KNO3. So don't turn one into one product and one into the other product. I say that all the time. You have to turn them into the same product. Both of these are water, because then you can compare which one produced more and which one produced less. Notice that the first fence produced less, the second fence produced more. What that means is that you don't have enough HNO3 to produce as much as you had for the KOH. So you had more KOH, or the KOH produced more product than the HNO3. So I didn't say that very well, but this is what I'm trying to say. This does not happen. You don't have enough HNO3 to produce that many moles of water, the 0.01, that's a bigger number than 0.007. So what that means is this is the most water that you can make, because at that point you run out of the HNO3. So now I can label that the HNO3 is the limiting reactant, that's the one we run out of, and that the KOH is the excess reactant. And since they were asking us about excess, I now know that that's what I'm going to focus on. I'm trying to see what is the concentration of hydroxide after I react this. So now what I did is I took that product that I knew I was able to make, and I said, well, let's see how much of the KOH was used up to make that. Because I know we didn't use all of the KOH because it was the excess, but I know we used some of it. So that's where I turned it back into KOH, and now I can see, since it was a 1-to-1 ratio, that this much KOH was used up. But that's not the question. The question didn't want to know how much was used. The question wants to know how much extra did you have. So now what we need to know is how much did we start with so that we can subtract them. So from the problem, I used the molarity and the volume of KOH to see how much KOH we started with. And then I can subtract them in this step right here to see how much KOH was left over. So now I know, after I do that subtraction, I know how much KOH was left over. But notice in the question, it said, what is the concentration? Concentration, and it was constant. We want to know the molarity of the OH minus. So two things. One is we need to get that to be just hydroxide, not KOH. And the other is we need to get it into moles per liter because they're asking us for molarity. So again, always look at the units that they're asking you for and see if you can figure out how to get your answer into those units. So notice in this fence, I turned it from moles of KOH to moles of hydroxide because in every KOH, there is one hydroxide, so it's a 1-to-1 ratio. And that gave me the moles of just the hydroxide, and then our very last step is to turn it into molarity. So we put two things together for this. We put two different volumes together, so make sure you put those two together as your total volume, because now that you've mixed them, your volume is the addition of both of those. Both of those came from the question. And then the moles on top that we just solved for, and finally we get our moles per liter. That was a really long, super hard question. So feel free to pause it and go back and look at that again if you need to review how to do that question. And that was both questions 1 and 2. And then I'm going to do titrations in my next video just to make sure that I have enough time to talk about that.